start. I don't know whether this is getting streamed on YouTube at the moment.
Yeah, Zunak, that's why the YouTube live is going on. Please go ahead, okay?
Okay, okay.
Yeah,
So,
let me know when you're finishing ending the streaming. Okay?
okay, I'll text you. Okay. Or
Sure,
call
sure.
you. Yeah. Okay.
Thank you, thank you.
Okay, so I know the announcements are being made saying that ma'am will be joining, but ma'am is busy, so you're with us, T's. The current week is week 4. Week 5 content has already been released, but tomorrow is the submission for week 4 quiz. So we will briefly go over the concepts that were covered and equations also maybe. And if you have any questions and all, you can ask the questions. I see 9 people here. 11, I mean 9 students, I guess. So if you have any doubts, you can ask here, or you can also use the discussion forum. I think one of the questions Nabamita asked, I did not answer or something, that we can discuss here. So this week we started with our discussion on laser. We continued it. So towards the end of last week, we started discussing about chirp. So and the first video of this lecture this week was about the limitations of direct modulation, and we also ended the discussion on chirp. Then we went ahead and discussed the random noise present in the lasers, namely amplitude noise, which is relative intensity noise, and phase noise. And while characterizing phase noise, we talked about the concepts of line width and how phase noise is a random walk process, and how the phase noise varies with time. One video was also dedicated to, I think, single frequency lasers. In the course, we have talked about only Fabry-Pérot cavities and lasers made out of those. So we briefly touched upon the construction of these different kinds of lasers, but the working principles are the same. And then we went ahead and started our discussion on external modulation. We started with phase modulators, then talked about how to characterize them, which this parameter V pi that causes a phase shift of pi. Then we talked about Mach-Zehnder configuration to convert the phase modulation into amplitude modulation, and we showed the graph of this cos square delta phi by 2, that graph that is also present in the assignment, I guess. And the last video of the week was about how much bandwidth each kind of modulation occupies. So we saw a few time domain waveforms and their corresponding frequency domain representations. And we discussed how we can compress the signals in frequency domain by doing some intelligent pulse shaping. So most of the concepts covered in this week are like captured in this list of equations. So this page is about all of the equations covering the noise in laser, and a few equations also carried over from the chirp discussion. Then we also went ahead and discussed about this. Then we also talk about the modulation. So the electric field output from the laser we model as this, and equation of chirp that you used for multiple problems in last assignment, I think. There, one question was based on this adiabatic chirp. Then we move on to discuss about relative intensity noise. We will briefly look at a few, a laser data sheet and what kind of numbers you can expect. These are the definitions and how you find that our working formula will be this one. I believe there is a question in the assignment based on this. And for phase noise, we use these equations, like we define phase error and how line width and variance of phase error are related, and how the time period of measurement is important in that process. Lorentzian PDF, I think we have mentioned in the lectures, but the exact equation of the Lorentzian PDF was not given, I guess. This is what a Lorentzian PDF looks like. Lorentzian function, you can say. We are not exactly talking about probabilities, but this is the form of a Lorentzian function. Then we talked about the phase modulation in electro-optic phase modulator, and converted that into electro-optic intensity modulation, and we applied this concept to explain how we modulate signals, either intensity modulation or modulating in both quadratures. So these are the equations for the week. If you want, you can take screenshots. Let us briefly see a few data sheets to see what are being used in our labs or applications. So this is a tunable laser. So you can change its output power as well as the wavelength of operation, and it is designed to be operated with the center frequencies prescribed by ITUT. So it is tunable laser source in covering this wavelength range. The operation is using these buttons. There are different specifications that you can use to purchase this. Like, there are different specifications, but you can see the typical line width is shown here as like 100 kilohertz is the typical line width. Then we can change the wavelength of operation in steps of 0.4 nanometer, which is 50 gigahertz. And relative intensity noise, you can see it is minus 135 dBc per hertz. So those are the parameters that we saw in the lectures, and you can see in real data sheets also. Then one phase modulator. It's not the datasheet for one phase modulator, but they're at their catalog. So it looks something like this, and they define the VPI value. That for this model, the VPI value will be 3.5 volt, which is specified in at a given frequency. So at higher frequencies, you might see this VPI value change subtly, and this phase modulator can you can opt to go for a phase modulator that has a larger bandwidth or smaller bandwidth or larger bandwidth. You can see phase modulators go all the way up to 33 gigahertz, even higher. A similar looking module will be the intensity modulators using Mach-Zehnder modulators. So you can see that the input laser power comes in, and we provide our electrical signal here in this RF port. So we will use a bias T to provide a RF signal that is shifted by some DC value. And the output will be taken from here. Extinction ratio they're advertising is they have extinction ratio of 40 dB. Optical power they can take in up to 500 milliwatt, and you can see these typical values. This is a table. So VPI values you can see this is 6 volt they're claiming. So you can guess from there that it's not a push-pull configuration. And you can go through this data sheet. Using these values, you can decide whether to use this component in your final optical link or whatever use case you're thinking about. And we mentioned in the class that they're responding to only they have a preferred polarization. So the input and output fibers are polarization maintaining fibers. Specifically, this in here, this is a panda type fiber that is the most commonly used polarization maintaining fiber. So I hope you've got a feeling for what kind of numbers you can expect. Here's the extinction versus here's the power level versus applied DC voltage. From here you can this is the cos square curve, but taken in log scale in the y-axis. So from here you can see the extinction. So these are three typical data sheets I wanted to show you. Now, do you guys have any questions about this this week's content? These are a few simulation results from simulating only phase noise for lasers. So you can see plots for given line width, and if you increase the total time, we're showing a constellation diagram. It gets blurred. For the same time period, if you increase the line width, you again get more phase noise you can observe in the constellation. And this is simulated random walk process that is being used to get the phase error values. And these phase error values are being used to calculate this constellation. Now, if you guys have any, the simulations are all being used. Simulations are being done on MATLAB. So we simulate like frame by frame. Like we assume that these are the electric field values for this much time period that we want to simulate, and then we go ahead and simulate how it would change. Okay. So simulators used for these plots are all MATLAB. If you guys want, we can share a few like snippets of MATLAB codes. PDF for this live sessions, I don't know whether you will have, but the videos are being streamed to YouTube, I think. I don't know whether it is being, the YouTube link is given on the course webpage. We can definitely provide them. Like you can go through these videos in YouTube. Is the coherence time? I'm not sure whether any questions are there about this in the assignment, but this coherence time coming from this is delta F is line width. And in the forum, I think in forum, Nabamita asked some question I did not answer. Let me check. Okay.
Junaid, I guess there is one more question in the chat box, which
yeah, spectral density of laser emission is given.
Okay, I think that is a assignment question.
We cannot directly answer assignment questions, but we can tell you how to go about it.
Yeah, how to approach it. Yeah, so we know that full width at half maximum is the power level at half the power. So if you estimate the width, if you estimate the power from that equation, you can maybe correspondingly estimate the width at 20 dB down. So 20 dB means it will be 1 by 100 of the power. So if you can estimate what is the width at half the power, you can estimate what is the power width at 100 of the power.
So basically, the form of the Lorentzian PDF is this. You have to use this, but you're not given all of the parameters. And this central frequency you can ignore for now. And what they're asking is this peak value you assume is something. They have given you the variation between these 2 points. This is full width at half maxima is given as delta f.
That f plus f naught, like in that Lorentzian equation, if you assume f equal to f naught, you can estimate what is a width at a, which is like represented, and then you can estimate what is at a by 100.
Yes. This is the question. Please give an example. No, you have to, there is no given formula, you have to do the hard work to find out. We can post an example on the discussion forum if you want, of a similar kind of question. It won't be the exact same as the assignments, of course. Yeah, we can post by tonight or tomorrow morning. We can post. Evening, you have to submit the assignment. Also, you can submit the assignments. You can submit partially, by the way. Like you don't have to wait to solve the whole thing at one go. Yeah, if you can solve 9 out of 10 questions, you solve those 9 questions, and 10th you can attempt later. Only the final like state of the assignment is what will be evaluated. So like don't leave anything till the last moment. If you can answer the rest of the questions, you just go ahead and do them. And the other thing that Namamita asked, I think, but I didn't answer because I kept forgetting. So there were like multiple steps of a question, but the one part that you'll be encountering frequently is like it is asking what is the change in wavelength given the change in frequency. So here you can like we always assume that the central wavelength is 1550 nanometer, and you use this equation, like, use this relation. So the question was based on how much does the wavelength change given a particular change in laser current. So from current, you have to find a change in power. This you can get from the either the slope efficiency or the long equations that were given. So from current, you can find the laser output power. And using that, you're supposed to find the chirp, that is the change in frequency, using what equation? Alpha h. I'm forgetting it, so I don't want to. I don't want to write the exact equation. I don't exactly remember, but based on the change in power, you can get the change in frequency. And once you get the change in frequency, then you have to convert it to the change in wavelength. That is how you're supposed to solve some questions about chirp last week. I think the solutions have also been released. I don't know whether all of the solutions are exactly the matching to the questions in the assignment. I think there are more solutions than there are questions. You can tell if there are mismatches.
Thank you, sir.
If there are any doubts, you can tell, or you can also use the discussion forums. Sometimes I get lazy and answers come late, but otherwise we are frequently visiting.
Okay, sir.
I'll try to post one example of this in the forum. Otherwise, these are the equations, I think. You were asked about constellations and modulation and all. It's a long assignment, but it's not too difficult, I don't think. Last week's assignment was harder, I guess. And I think last week's assignment was hardest among all of the assignments. If there are no questions, we can close.
Okay, sir. Thank you, sir.
Okay, let's close.
No, I think there is, yeah, one more
Oh,
question.
okay.
Jagannath.
Yeah, ask.
Yeah. Either you can ask or type in your chat.
Can you I don't know if my, okay, wait. Let me check first and then. Okay, like I was afraid that my screen, NPTEL course page is not visible on my end, I hope.
Sir, you are not audible. Hello.
Hello.
Yes,
Does
sir.
it-
It's
okay. You're still seeing that Lorentzian shape, right? Not
Yeah, yes, sir.
okay. Question number 20 is making you derive all of the how you arrive at the uh, intensity as a function of input voltage. To arrive at that, while during the discussion on MZM, you have phase modulators, and the output of the two phase modulators are being added to finally end up at a result with the intensity, where the intensity is changing as a function of the input voltage, simply by using phase modulation in like one arm of the Mach-Zehnder configuration. I think ma'am has gone through this all of the steps. There, one of the steps we are asking you to change. So not so both of the arms are not having the equal amount of power. That is the change. So that is what is being asked in question 20.
Okay, sir.
So it
The
is,
equation is already given in the question, right? You have that electrical equation for the
yeah,
phase modulator.
yeah, but there is no shortcut or anything. That question
No
is,
shortcut. It's like you need to derive what will be the electric field for the maximum and minimum output power case. You need to see how the phase modulation will give the output fields and the corresponding power in terms of heat.
yeah, that is how you solve it.
Yes, sir.
Make some assumptions which says what will be the maximum output power and the minimum output power. What should be the phase so that the output power is maximum and minimum, and then you will get the equation.
I mean, it shouldn't be too hard now that I read it. I expected it to be harder, but all of the information are present in the question only. You don't have to go back and watch videos, I don't think. Okay, if there are no more questions, we can end today's session. For discussions and announcements, like keep an eye out on the announcement page and the Google group for discussions. That's all.
Okay, sir.
Okay, let's close.
Okay. Okay, sir. Good night, sir.
Thank
Good
you,
night.
sir.
Thank you for the
Hope to see you next week.
Thank you, sir.